So let's start talking about this idea of limits here using what I call the calculus conundrum. We saw in topic 1.1. We saw in our previous topic where we started talking about this idea of instantaneous rate of change. We saw that we can approximate instantaneous, meaning at an exact moment, rate of change of all kinds of nonlinear functions using delta y over delta x, our rate of change, or what you learned was slope back in your early algebra days, but using change in y over change in x, we could approximate instantaneous rate of change. And the thing that made our approximation better was using very small delta x's, or very small changes in x. So the question that we're kind of left with is, what's the smallest change in x we can actually use? It would be nice if we could just use a change in x of 0. Unfortunately, we know we can't divide by 0, so we can't just let delta x equal 0. We're not going to be able to find rate of change that way. However, calculus gives us a tool. We're going to use this idea of limits. And limits allow us to evaluate things as we get close to a value. So we're going to use limits to evaluate delta y over delta x as delta x approaches 0. And that's really what we were doing in our previous topic. We kept getting delta x smaller and smaller and smaller. We kept moving it closer and closer to 0. And we were seeing that the rate of change was kind of converging to a single value. And so limits will allow us to actually evaluate those changes in y over changes in x as change in x gets close to 0, rather than having to build these long, tedious tables where we're just making delta x smaller and smaller. Limits will actually allow us to evaluate what we were trying to do in topic 1.1.